Hello, everyone. My name is Clay Stevens, and I'm a fourth-year PhD student at the University of Nebraska-Lincoln. Today, I'm here to talk to you about our new approach to improve the efficiency of repeated formal verification by combining solution reuse and bound tightening to make the problem a bit smaller. As a bit of background, here we're talking about formal verification of systems that often start with some sort of formal system specification. That gets translated into a more formulaic logical representation, which ultimately gets turned into a propositional formula, often represented in conjunctive normal form, which gets fed to an off-the-shelf solver to find any solutions or counterexamples that satisfy the system specification. Oftentimes, this is a rather expensive process, and that only gets exacerbated when the analysis has to be repeated because the system specification changes. In most cases, if the system specification were to change, you would have to repeat the entire analysis process again on the entire specification. To do that over and over and over is, of course, too expensive and doesn't scale in most cases and can be often intractable and therefore not used. As a bit of a background to this, one of the ways that the community has attempted to make these problems more tractable is to introduce the idea of bounded verification. For relational specification, what that means is that the translator will define two relational bounds on each relation used as a variable in the problem. The first is the lower bound, the values that must be assigned to a particular relation, and the second is the upper bound, the values that may be assigned to the relation. In conjunction with each of these lower and upper bounds being assigned to each relation in the problem, we can map out the entire search space in terms of what values are going to be assigned to which variables in the problem. This allows us to have a finite area to explore, which makes the problem soluble in the first place. This is important for repeated analysis as well, because one of the main approaches to improving repeated analysis is to tighten those bounds for subsequent analyses of the changed or evolving specification. By tightening the bounds, we can reduce the size of the underlying SAT problem and therefore make the problem more scalable and easier to solve with each subsequent iteration. The way this usually works is that we'll try to extract information from the solutions from a previous iteration of the specification, use that to tighten the relational bounds, which therefore translates into a smaller CNF problem and a smaller problem given to the SAT solver. The problem with these approaches, is that they require existing domain expertise on the part of the developer of the verification tool. They are only applied to certain problems. For instance, Titanium and Flare can only apply to analyzing Android applications. So they're not generally applicable. They won't help with any other problem, just the one that they were designed for. On the other hand, more general purpose solutions often try to reuse some information from the prior solutions and limit the size of the problem by completely skipping portions of it. These can use either full solutions or partial solutions and have been used in a variety of different ways. The problem with these, though, is that in order to be general purpose, they have to be based on some structural information encoded in the solution itself. That often leads to being a very low-level kind of cache. And so any sort of change to the system, no matter whether it's irrelevant at a high level or not, is going to lead to a missed opportunity for reuse. So that often limits their applicability in practice as well, as many formal specifications are not going to be designed in exactly such a way that makes the caching easy. To resolve these problems, we leverage the particular insight of ours that these systems often involve in predictable domain-specific ways, which we call operations. For example, a system may evolve by adding new components or changing the multiplicity of a database table or something of that nature, something that's predictable and can be defined in a particular formal way. So long as we have these operations and we can express them into the system, we can extract that information and leverage that domain knowledge to improve the verification performance. So the way we do this is with an approach that we call SORBOT, which stands for Solution Reuse and Bound Tightening. SORBOT is essentially a two-step process. The first is that we take the specification and a formal description of each of the operations that can be applied within that domain, and we perform what we call a speculative analysis of each operation to find out what its ramifications would be upon the specification itself. So this is only done one time for each operation. what we do is we analyze the operation and find out what the impact on the relational bounds will be. And any bound that is not changed by a particular operation is termed fixed and is stored for future use. The second step of this is the actual repeated verification itself. So once we've determined which bounds can be fixed, we can use the specification and the operations to perform the verification upon the specification to generate the solutions, and then feed those solutions back into the system along with the specification, the operations, and the fixed bounds to do our loop of repeated verification over and over and over. Describe this a little bit more in detail. First, the speculative analysis starts by taking the specification, which we know has a default search space based on its default relational bounds. We feed the operation into the speculative analysis component. And for each operation, we can then use the same underlying SAT solver and the same underlying formal analysis technique to determine what the impacts of that operation would be on the resulting space of solutions generated by that specification after applying the operation. We then compare that to the default search space, and we see what has changed. So in cases where the bounds do not match the bounds of the default search space, we know that there's some flex there and that the operation might change them. For the ones that are not changed, however, the bounds that are not affected by the operation, those we term fixed and we store for future use. Once we've done that, again, once for each operation, we can then actually get into reusing these to tighten the bounds. So the first thing is we will get our initial analysis. We have to start somewhere, of course, get our initial analysis and compute the solutions. And then as we apply the operations to the specification, we'll look up each operation in the database of fixed bounds we computed in the previous step. And in this case, we've determined that that operation corresponds to a fixed bound of the lower bound of relation 1. We can then examine the solutions we generated the first time, which count as sort of points in our search space. And we can combine knowing which bounds are fixed to using the values stored in that solution as those fixed bounds for future analysis. What that allows us to do is it allows us to greatly trim the search space because we can ignore any part of the default search space that is outside those new bounds based on what we have from the previous solution, because we know that the fixed bounds will not change. So whatever we had determined originally before the operation will still be true after the operation. Now that we have a trimmed search space, we can get the same benefits that the other state-of-the-art approaches do, in that we end up with a smaller CNF problem and a smaller problem passed to the solver, which is exactly what we want. So Zorbot in this case applies solution reuse in that we examine the previous solutions to find which bounds can be fixed. With no low-level cache lookups, all we have to look up is the operation in the list of fixed bounds, and we can apply bound tightening without having any prior domain expertise or encoding it into the tool itself. So Zorbot can be used for any problem as long as we can get the operations and the specification defined in the appropriate way. We then evaluated our implementation of Zorbot to answer a couple of questions about it. First, we wanted to see how effectively it actually reduces the search space, because that's where we get the actual benefit out of the approach. We wanted to see what the performance improvement is, and we wanted to see how much overhead this introduced, because if it's too costly to do the speculative analysis, it won't be a good tool. As measures, we counted the number of primary variables in the underlying solution. They're the underlying problem. We actually measured the running time of each verification, and we measured the wall clock time it took to run the speculative analysis. We compared Zorbot against an unmodified alloy analyzer version 5.1 against Titanium, a previous approach that uses the bound tightening, Platinum, again, another bound tightening approach, and iAlloy, which is an approach that uses the solution reuse in particular. Unfortunately, we were unable to get Platinum to work, and so it had to be excluded from our results. We then applied each of these baselines against 16 alloy specifications from across 4 different software engineering domains drawn from the literature. We had some bundles of IoT apps, which came from a paper known at ISTA from 2020. some data models extracted from some Ruby on Rails applications, an access control system using role-based access control, and the Android apps that were used in the Titanium paper back in 2016. First, we wanted to see how well Sorbot can do at reducing the search space. So this is compared against the CNF problems that were generated by the original Alloy Analyzer version 5.1. We took the mean number of variables, is what is represented here, and the mean percentage reduction point to point for each solution as we apply a random set of operations. As you can see, we reduce the size of the CNF problem in all cases. In some cases, dramatically, of almost 100%. We reduced many hundreds of thousands down to simply hundreds for the larger specifications. And what this translates to is less work for the solver. So we know that Sorbot can reduce the size of the problem and that will give us benefits each and every time we want to analyze a new operation. So that's good. For our second research question, we computed the running time for verification of a series of sequentially applied operations against all of our baseline systems. We have a lot more graphs in the paper, but just as sort of a summary, we found that Sorbot is commensurate in terms of running time with the other approaches. It's often better than the others, and in cases of the large specifications, such as the Alloy app, the IoT app bundles, it outperformed all of the other approaches. For the smaller models, it was less so, in part because the reduction in the size of the problem was less. There are fewer variables, or fewer variables to reduce. Lastly, in terms of the Android apps, which came directly from the Titanium paper, Titanium outperformed Sorbot on those, which shouldn't be too much of a surprise since it was optimized for those particular papers in those particular specifications in its own paper. In any case, Sorbot outperforms the baseline Alloy Analyzer in all cases, showing that there is a benefit to doing this compared to simply reanalyzing the entire system over and over again. For our last research question, we just counted up the overhead and timed how long it took to do the speculative analysis of each of the operations for each of the specifications. And it was very small, only a few seconds in some cases, such as the IoT specifications, where we're saving thousands of seconds per verification. So this is a one-time cost that gets paid and amortized across all of the savings that we have for each of the analysis. So in total, it counts for a very small percentage of the running time. So in summary, we introduced the new approach called Sorbot, which reduces the cost of repeated formal verification by leveraging the domain knowledge contained in domain-specific operations that describe the kinds of changes to the system that will be happening. Sorbot is the first approach that combines solution reuse and bound tightening instead of simply using one or the other. Sorbot outperforms the baseline Alloy Analyzer and is on par with or faster than all of the other state-of-the-art approaches as we compared it against. And it performs all of this benefit with very little additional overhead. Just as a last note before I sign off, I will be on the market for a tenure track line in software engineering in the fall of 2023. So if you happen to be hiring any new software engineering professors, please keep me in mind. And thank you for listening.